Got this up and running. It's a new atmosphere shader, and I kind of solidified a workflow for converting shader toy GLSL into Unreal Engine HLSL, so that you can kind of go find an effect you like and convert it, which is where I got this one. So now we have a new atmosphere effect. I think it looks really good. I think this will probably be the last one that I need to make. Um, I mean, you can kind of see what it looks like right now. I did kind of fly into the far side of the planet, so let's just do this. But we get scattering, multi-scattering. This is a MIT licensed thing, so just have to credit it in the project, which I will. And basically, with this, we get a full-fledged, fully functioning, accurate, realistic scattering atmosphere shader. You see, we're getting the distance fog here. We get different daytime colors depending on where we're at on the planet, just like it's supposed to. A blue sky during the day, right? And then we get like our sunset colors over here. And even on the night side, we get a little bit of ambient contribution. Although I have it turned down probably too far to be able to see it. But, so we can also do things like go down here to the surface. Yeah, let's open our editors. Change our various parameters about how the sky looks. And it should all update realistically. Woo! We have a set of, like, these are the parameters that we use to drive it. Offset moves it up and down, basically. Planet radius is self-explanatory. Atmosphere height should be pretty self-explanatory. This is how thick the atmosphere gets. And all the rest of these do stuff as well. Like we can change the height the Mie is rendered at. We can change the height the Raleigh is relative to the rest of the atmosphere. Change the light intensity. Change the light color. So yeah, I'm pretty happy with this. And this is the result. I don't know if you're familiar with what Shader Toy is. Shader Toy is a website where people upload basically a bunch of open source GLSL, OpenGL shaders. And I've struggled with converting those to use them in Unreal before, but I have a workflow now that I think is at least reasonably reliable. Like, I'm pretty confident that I could convert things as they need to be. And I thought that it would be useful to kind of go over that and go over the how that's reflected in this atmosphere shader, how all this works. So the difference between using like a HLSL node and just a regular material is that the HLSL node is like basically shader code, right? So you can use it in conjunction, which is what we're doing. Um, so to start with, I should have. Okay, yeah, I got a coworker to format this guide for us. So to start with, let's see what Shader Toy is. So here's the website Shader Toy. This just has GLSL code, right? That people have written. This is not the one I used actually. This is a different one. Um, this is the one that I used, the atmospheric scattering that I converted, right? So basically, We'll grab this whole thing for reference so that we can pull it up side by side. All right, so here is my refactor, and here's the original GLSL. So it's not the easiest thing in the world to convert these, and I wasn't able to find many good sources on this, which is why I thought that it'd be useful to put up a video on how I managed to do it. Because when I was looking for this, I had to find this on like kind of an obscure forum where somebody was talking about doing it, then kind of blunder my way through it. But I think that now I could do it again, and it would be a lot easier. So first of all, there's some differences in syntax, and you want to take care of those first. So you got here, you got vex, but in HLSL it's floats. So vec2 would be equivalent to float2, vec3 would be equivalent to float3. And what you can actually do, what I tend to do for this is I just open up a find and replace in the document, go through replacing every vec2 with float2s, same thing, go through replacing every float vec3 with float3. Again, float vec4 with float4. All right. Then what you want to do is look at any instance of instantiation. So let's pull that guide up again. So you basically replace all these because these are going to be common. There's also in GLSL you can instantiate a vec3 like this, and all three fields will get 0, but you can't do that in HLSL. So you got to find every place where like float3 open paren is, and make sure that they're all fully qualifying the initialization. Okay, next, and this one's the pain in the ass step. Each function needs to be standalone. So this is actually a great file to use as an example, because if we look up here at the top, you'll see they defined a number of constants to use here. You can't do this with the way it works because all of this is going to get wrapped in a struct, and you can't do this inside of a struct, and you can't use the external context inside the struct either. So what you have to do basically is change from any functions that would be using these values, right? You need to pass those values in through the function signature. So like, for example, should be pretty easy to find one. So like right here, right? This skylight function. We can't use it like this because it has all these values that are expected to be defined externally. We can't do that. So you would pass in to this atmosphere radius, planet position, planet radius, atmosphere. Oh, well, um, this is this would change, but yeah. So 3 times atmosphere radius, planet position, planet radius, atmosphere radius, ray beta, me beta, absorption beta, ambient beta, g, height ray, height me, height absorption, absorption fall off, primary steps, and light steps. So these are all those constants that were defined above. Well, we would need to add inputs to this function for each of these so that they can be passed in. And what makes this a pain in the ass is that then you also have to find every place where this function is utilized and change it to also pass these into it. So what I would suggest, if you have a function that you're converting and it has quite a bit of constants like this, is to just assume that you're going to pass all of these constants first to every single function. So your function would start like fn 3 planet position, float planet radius, etc., for each of these. And once you create that set, so that you're sure that you're passing it in the same order on, I would add it to every function. Since you know you need those constants, you just put this on every single function, and then for the function specific stuff, you can put that at the very end, and then you will have the same signature for all your functions, so it's not too bad. um, so let's go ahead and get rid of that. Okay, the next thing you got to do after you've updated all your function signatures to pass in all the values they need so that they can all be self-contained. Basically, each function should be standalone. It shouldn't require any external like values or anything like that. You should pass everything it needs to it, and then it does the thing and returns your stuff back. Usually in the shader toy GLSL, it's also doing camera controls and other kind of like scene rendering stuff. So you want to remove that stuff, and anywhere where it was using that camera for a position, you want to be passing in like camera position, um, camera direction, camera vector, things like that that were calculated from the camera. Um, Inside the code, you can actually strip that stuff out and just pull that stuff directly from the Unreal Engine camera. You may have to flip vectors too. Like I think I had to multiply my camera vector by -1 for it to be pointed in the right direction for my functions. Okay, finally, most of these shader toy functions, I think probably all of them, should have, because it's the format, should have a main image function. And it's usually formatted like this. You've got your frag coordinate for your screen pixel, and then you've got your out frag color. Well, we don't use the out in HLSL, so instead you change this to a float 4. Get rid of this input. You can still input this if you're using it, but for instance here, the only place where they're using this is to get the camera vector, and for me, I could just pass the camera vector in, so I just did that. So this is the function that's usually rendering the effect. Like I said, there's a bunch of camera stuff here that we can strip out because we don't. Our camera will be controlled by Unreal, so we don't need to be like animating camera positions and things like that. Finally, go see what is actually going on in this function, make sure it's all implemented, make sure any function calls that it's making have all the new updated values. Like right here, it's passing in all these, which luckily this one just worked that way to begin with, but some of the other functions didn't. And then finally, return, once you've manipulated your return color, and you're done with all your operations, you just return it. So let's pull this back up. So you go to your main image function, you clean it up, you replace the out float parameter with a return type of float 4. You create an internal float 4 variable to replace any operations that were happening to the out float 4 variable. And then you return this variable after it's done. Okay, so once you've updated all of that stuff, you need to go wrap your entire bracket of functions, all your functions, with a struct. And you can call it whatever you want, but this is what allows you to utilize a function library and have the functions have references to other functions within them. I'm not sure of a good way to do this outside of doing it this way, unfortunately. And then finally, you can create outside of this, like after this function's been defined, you can create an instance of the struct, and then you can invoke the main image on the struct with whatever arguments you need. So that kind of covers the code changes, and with that we can kind of take a look here. So we can see, like for instance, Skylight has 4 inputs here, but if I go over to my conversion, we can see we have a struct of atmosphere functions. This is passing in everything it needs. It's not relying on any external values. Likewise, this is passing in everything it needs now. It's not just passing in 4 things, it's passing in everything it needs so that it doesn't have to rely on any external values. It's doing the same stuff, just with the passed in values instead of the constants. Same thing, this invokes a couple of other functions that need lots of these values, so we have to like cascade them down to it. So this render scene method gets all the extra things, and then main image gets everything. All of the possible things that we need for all the other functions happen here. Um, we This is just the same main image function that there was over here, but updated to take in a lot more parameters instead of just float 4 in float 2. Um, we now don't take any of that, but we do take all of these values. And you don't have to define these inside here. That's not how that works. So you can see we're invoking it. We have all these values, but we haven't defined these values anywhere. Well, that's because if we go up here to our material, when you create a custom node, you can look that up in the material editor by just clicking custom. It comes in like this. So we pick an output type of float 4. We paste our code, our updated code, into this block. And then for each of those input values, each one of these, so let's take a look at camera position, right? We add an input. Etc., etc. So we go through each of our inputs and we add an input to the function itself. So these will be defined in scope by as whatever values they're defined like externally here, right? So when we plug stuff into these, that's the value that's going to actually get passed to that main image method. So you can see I've done that here. We have all the parameters that we have to get and derive. For instance, we need scene color. We get that from post-process input 0. We need scene depth. We actually get that by distancing that's absolute world position from the camera position. Um, we need the camera vector, which you can see I've multiplied by -1 here because I think they might be flipped. It was required to get it to work properly. Camera position, world pixel normal, world normal, skylight mode, like everything that we've defined that goes in, we define out here. We set up all our default values out here. And then once we're done doing all that, we create a material instance for it. We go to our scene, we create a post-process volume. We go to our post-process materials array, and we add our material instance, and that's what allows us to go mess around with it in real time. And then we can kind of figure out what makes it tick by changing values here, right? Let's go back down to decreasing or increasing the light intensity, changing the absorption color, changing the Rayleigh beta, which is what changes our like atmosphere color. So if I change this to very blue, and then I change my light to like more yellow, then we start to get green. You kind of see what's going on here. Planet position defines the center point. Planet radius defines the radius of the planet we're looking at. And yeah, so that's pretty much it for this one. Like, it's a really cool effect. There's a lot of really cool effects on Shader Toy. Like, I'm probably gonna look into seeing if I can replicate some of the nebula effects I've seen on here. It's fun to just kind of browse around. You can change the code inline to test it. This one's probably not performant enough to actually use it, but yeah, you can kind of. So, like, if we wanted to convert this guy, we would come in here, change these defines, right, to be inputs into all our functions that use them, change all these functions. Yeah, see, like this kind of stuff um, could either be defined in line of wherever it's used or it could be defined as an input. And then finally, once we'd converted all of our functions to be standalone and we had um, put them all in a struct, along with converting the main image in the way we talked about, we would have to come down here and invoke our main image function, and we'd be able to get this in the viewer. And we probably have to do some kind of blending with the scene color, you know. But yeah, let's look at some more. See, like, okay, this is a cooler black hole. Wait, what? Oh, he has. This would be more complicated. I'm not sure how you would go about converting this yet. I don't have a workflow for this. I have a workflow for specific, um, for like a single file conversion. I'm not sure how to handle the multiple buffers. We would have to come up with a creative solution for that. But there's a lot of cool stuff on this website. You can learn a lot. It runs kind of slow sometimes, which is understandable. This is GLSL running in the browser. Hopefully, I didn't just lock it all the way up. No, there it goes. Not all of these are great. Too expensive. But yeah, so you can kind of use this idea, this workflow, to find stuff on here that you like and port it over and have it rendering in Unreal. Most of these seem to be doing some form of noise plus sphere trace. But yeah, that's it for now. I just wanted to kind of demo this progress I made on the atmosphere shader. I really like it. I think it looks really good now. and kind of put it out there how to do this kind of shader toy conversion because it's probably going to be pretty useful for me. It's already been useful with being able to get this atmosphere working. It's got a really nice like distance blending that I like quite a bit. No crashing. Okay, it didn't crash. I also like this because you can still see the planet rings even during the daytime, which is cool, I think. But yeah, so if you ever want to convert some GLSL to shader toy, I mean, some shader toy function to use it inside of an Unreal material, hopefully, this will at least get you started down the process to doing that. Keep in mind that when you finally connect all the inputs up and you connect the output and it tries to load it for the first time, you're very, very, very likely for it to not work the first time. Because what I've outlined here are the most common things that you have to change, but they're not the only things. So, for instance, um, in GLSL, LERP is called mix. So if you have mix calls, then you would need to change those to LERP calls, right? But it will give you errors, and usually they're pretty good. Um, so you basically, once you've done the top level, like broad conversions of everything, and you think that you got it right, load it up, try to run it. You'll get some errors. Go through the errors one by one and fix them. And then before you know it, you'll have something loaded and working. And then once you've got it loaded and visible, then it becomes a lot easier to kind of debug any issues that arose from it, anything that's wrong. Like, and ooh, I crashed. Like, for instance, for me, I had to flip the camera normal and the light direction vectors because it was expecting them to be pointing a different way than the opposite direction than they were uh, from just doing them the way I was calculating them. Excuse me. And yeah, so I'm gonna kind of call that for now. If you want, I will show. Um, let's see. I can just briefly scroll through this entire class so you can see it. If you wanted to be able to reproduce the atmosphere shader I'm running here, so I commented out all of the constants, but I didn't delete them. I wanted to keep their initial values as defined here for reference when establishing, default values for the effects. So you can see we've wrapped our functions in a struct. This is really important. It's the only way you can get a function library going. We've got our calculate scattering method here, and this does the whole shebang, Mie, Raleigh, multi-sampling, sampling, and whatnot. And finally returns a color, and then that's used in a couple of places. One is in the skylight. This is effectively casting some light on the ground, some light contribution from the atmosphere. It's what's giving us like our fog effects and things like that, right? So, ending. Well, Eventually, we will get to like proper ship physics and whatnot, but right now we just have a little flying orb that's good enough for us to test things with. All right, so I'm just gonna try to scroll briefly through each one so that you can pause it and look at any code that you're not sure about. I might also paste this in the description of the video whenever I upload this. Render scene. Finally draw the atmosphere. This is our main image that I was talking about. You see how we're turning a flip 4 here. We updated everything. We invoked render scene, and then we invoked calculate scattering and appended it to this color that we created up here. And finally, this is applying exposure, and I trust them. I didn't know this is how you apply exposure. So, and then finally, we return a flip value for this. And then out here, so like most of the time, these shader toy functions invoke this main image function in order to render the actual effect. So usually you would be out here creating your struct and then invoking main image off of it. But the beauty of this is that if you didn't do it like this, you would not be able to say invoke render scene from inside of main image. You just wouldn't be able to do that because the way the custom node works is kind of janky. Um, what else? What else? What else? What else about this? Um, Not too much. Let's try volumetric nebula. This is a pretty nice looking one. So we could convert this and probably get it running in Unreal faster than it runs here, most likely. Um, all right. I'm gonna end it there. This is just like a quick overview of some of the progress I made yesterday. I spent like probably 8 hours getting this thing working all the way. But now it does. I'm quite happy about that. So yeah, later. I actually have next up. I have a refactor on my plate. I'm gonna be working on refactoring the mesh generation to occur at the node level in my planet actor. So instead of having the planet actor manage a queue of mesh updates, each node is going to contain a chunk, and it's going to be responsible for rendering its own chunk when its state changes. And so I'll probably be working on that for the next couple of days. And that's it for me. Later.